Okay, I think we can get started now. So welcome to IMO Showcase number 6. So today we will have 2 speakers now in the afternoon, and we'll have the IMO Showcase number 7 in the evening, which will be the last one. So the IMO Showcase number 6 will have 2 speakers, just like I said. The first speaker is Wei Luo. Wei has been with us at the camp since the beginning, 2023. He is a very famous Olympiad coach in China, and let's welcome him.
Thank you very much. Today I'm going to talk about the IMO 2019 problem 3. The problem says like this. A social network has 2019 users. Some pairs of the users are friends. And the friendship is mutual. When A is a friend of B, B is also a friend of A. And we have the following events. It says, starting with, you have 3 users, such that A is friends with both B and C, and B, C are not friends. We change the friendship status. Then B, C are now friends, and AC and AB are no longer friends. So that's a kind of operation on the friendship relations. Initially, we have this many users have this has this many friends and etc. Then the final step is that we want to prove we can operate in a way such that at last each user is friends with at most one other users. So it's easy to see we should describe the problem by a graph. The user should corresponding to a vertex. Friendship corresponding to the edge. In the graph theory, something happened. I hope you remember the problem. It says we have 2019 vertices. And in the problem, we know how many friends some of the users have. So we have this many vertices such that they have 1009 friends. That means in the graph theory, the degree is equal to 1009. And you also have this many vertices. The degree is 1010. And in this operation, in each operation, it says it's between 3 vertices. Initially, the friendship is like this one, the connection like this one. There's no connection between B and C. Then you change that, change every connection to this one. Then the objective is each DI should be no more than 1. So start with a lot of DI being large, then you end with each DI less than 1, no more than 1. Since in each operation you should have some vertex with degree at least 2. So if you reach this step, you can no longer operate in any way. How can I reconnect this one? Okay. So let me summarize the conditions of the problem. The number of vertices and the degree information, and the operation is like this one. And the objective is each DI belongs to 0 or 1. Now let's analyze the problem. We can find out that in this operation, you see the degree 2 vertex change to degree 0, then degree 1 vertex change to degree 1. So the degree modulo 2 is invariant. And we also find out that before this operation, you have 2 edges. After that, you have 1 edge. So the number of edges is decreasing. And another seems to be trivial fact is you have at least 1 edge left after each operation. So take into mind about the properties of this operation, then we can consider the problem further. Let's see something that can happen in your operation. We want the operation to last to the final step. So we need to avoid some situations that we cannot operate anymore, but still not the last step. One of the possible trap is that you have a component which is a complete graph. Then you need a missing edge in your operation. So when you have a complete graph, you cannot operate on this component. And the other one comes from the degree is invariant modulo 2. If you have some component such that the degree of each vertex is even, then after you operate, you notice that your final step wants every degree to be 0 or 1. So for a vertex which has degree even at the beginning, it should go to a vertex with no edge at all. So if some component, if the degree of some component are all even numbers, then the final every vertex in this component will have degree 0 at the final step. That means you have no edge for this component. But we have mentioned that you have at least 1 edge after the operation. So that gives you a contradiction. So actually, for any component which is of even degree, such that each vertex have even degree, it will not go to the final step. So that's another kind of situation we need to avoid. That's some component with all even degrees. So that's something we need to avoid. But things is not that difficult for our concrete problem. We have some vertices of odd degree, a lot of vertices of odd degree. So the way we want to deal with that kind of trap is we notice our original graph is connected and has many vertices with odd degree. So we try to maintain this connectedness in our operation as long as possible. Here's a proof that the original graph is connected because the sum of two vertices, the sum of the degree of 2 vertices is already at least n-1. So if 2 vertices are not connected, then they have n-1 edges going out from these 2 vertices to the other n-2 edges. So there will have a common vertex connected to both. Then they are connected in at most 2 steps. So then our strategy is to maintain the graph to be connected before we have a tree. So in each operation, the number of edges is decreasing. So as long as when you get a tree, then the further operation will make the tree disconnected. You don't have enough edges to maintain the connectedness. So here some basic operation. We know that it's when we have a connected graph, you take a cycle, you delete one edge, you still have a connected graph. So it's a similar operation there. You see, you start with W, V1, and V2. You operate on W, V1, and V2. You look at V1 as the A there. Then after operation, V1 is disconnected with V2 and W, and W and V2 are connected. But if we assume that V1, V2 are on a cycle, and then V1 you have another path connect V1 and V2. So after this operation, you still keep the relevant vertices to be connected with each other. So we are looking for such thing to be operated on. So then we find a cycle. We try to find a cycle and find some vertex outside the cycle, such that the vertex outside the cycle is the vertex W. It's connected to one vertex of the cycle, but not connected to the next vertex on the cycle. So let me go to the next page. How do we find such a cycle? We actually, let's assume the graph is, we start with a graph, which we actually prove a more general case for a graph which is connected, which is not yet a tree and not a complete graph, and some vertices have odd degree. We want to operate on this graph. We are going to prove that we can operate on this graph. Find a maximal cycle. Why we find a maximal cycle will be clear later. If there is a vertex W not on the cycle, you know, by assumption, the graph is connected. So W should be connected to the cycle in some way. And go along the path. Then the last vertex not on the cycle, we call it W prime. Then this W prime is connected to some Vj on the cycle. It's necessarily not connected to the Vj minus 1 or Vj plus 1. Otherwise, when W prime is connected to Vj and Vj minus 1, you can have a larger cycle containing this W prime. So that gives you a situation we can operate on. That for the case that the maximum cycle doesn't contain all the vertices. For the case the maximal cycle contains every vertex, then you want to find something you can operate on between 3 vertices on the cycle. So this is your maximal cycle, and assume it contains all the vertices. You want to operate on them. The operation depends on 2 adjacent vertex on the cycle and another vertex there. Let's say Vj, Vi minus 1. We need this Vj is not next to Vi and not next to Vi minus 1. And we also need this Vj have one connection with Vi and Vi minus 1. So connect Vi, but not connected to Vi minus 1. Then you can, after your operation, you erase these 2. And you put this line here. You still have a connected graph. In order such a Vj to exist, you see this Vj should have different connections with adjacent vertices. The contrary case is this Vj have the same connection with every 2 adjacent vertices. So it tells you either this Vj connect to every vertex, not every vertex not next to itself, or this Vj have no connections with any other vertices. So if you have such a case, then almost all other vertices will have degree larger than 2. Then you will not have this case. If you have only this case, then the whole thing is a cycle. So it's eliminated by our assumptions at the beginning. So that's the last piece. If the cycle contains all vertices and there's no good we say such operation is good operation. If the cycle contains all vertices and no good operation, then each VI should have degree n-1 that's connected to any other cycle point or degree 2. And in both cases, except the piece is have 3. The blue one, there's a case, the blue one, that 2 of the vertices have degree n-1, 2 of the vertices have degree 2. So that's not covered by this, not a contradiction, but still you can do it by hand. So in any case, we actually proved if you have original graph such that it's connected, has many, you don't have many, I think it's the next. Yeah, if it's connected, not a tree and not complete graph and has some odd degree, you can operate to maintain the connectedness. Then you can, when you maintain the connectedness, every other, you have odd degree, this property is maintained. Not a complete graph is maintained, and not a tree. You only possible exit is you reach a tree. So then after operation, you finally get a tree. Then we can see what can be done for a tree. Okay, for a tree, we actually do inductions. Pick a leaf of the tree, and V1. And it's connected to some point V2. If V2 is connected only for one V1, just for V1, in some cases, the V2 is itself a leaf, then you don't have to operate anymore. If V2 is connected only, is not connected to any other leaves, then you operate on V1, V2, V1, and another point connected to V2. Then you get that one, you have a isolated vertex. And another piece, V1 is connected to the V3 part. The V3 part is a tree, and V1 connect to V3 part, you still get a tree. If V2 is connected to more than one leaves, you take the operation V2, V1, V2, and V3 to get a component with only one edge, and another part is a tree. So in both cases, we get each component to be a smaller tree. Then you can do this operation until you either get a component to be isolated vertex or a tree of just one edge of 2 points. So that should finish the proof. The main idea is 2 steps. First, use good operations to reduce the graph to a tree. Then you eliminate leaves one by one on the tree to get the small pieces. So that finished the proof. Actually, I think I could give you another example of proving similar theorems for a general graph. There's one theorem says any connected graph can be partitioned into, let's just write as something like this one. It's 2 pair of edges with common endpoints with at most one edge left. You can use similar ideas. Reduce the problem of this graph to the corresponding problem for a tree. For each tree, you look at the leaves. Depending how many leaves you have even number of leaves. Then each time you take out such V shape to make this, to eliminate all these leaves. If you have, for this case, you have odd number of leaves, you take split them in this way. Yeah, so I think that's all I want to say.
All right, let's thank Wei for a wonderful talk. If you have any questions, please. Please raise your hands if you have any questions. Questions? Okay, if there are no questions, let's thank Wei again.